So you just need to remind yourself, yeah, in geometry, good. So you have done that. So just need to remind yourself how you did that. That is how we are doing it. And of course, the idea is that this is the idea of the screw. You are moving the screw up towards from A to B. Or you can also use the right hand screw rule that you assume you are holding a wire and your hands are moving from A to B. So they are moving from here to that. Anyway, and the thumb is facing up. That would actually represent the direction of the cross product. So what I have also said about finding out the basic properties, we have seen that cross product does not follow the commutative law. In fact, it is anti-commutative. Number two is that it is not associative either. So A cross B cross C with a bracket between B and C is not the same. The idea is that they are not the same with A cross B with a bracket with A and B cross C. So again, distributive, yes, they are distributive. A cross B, you can either do this plus this one, and then you cross them, or you can do them individually, this one and this one alone. So the idea is right there. Allow me to take a sip of water. And scaling can be done by either doing it with one or with both. So you are saying that you can do scaling. That means multiplying with a scalar. Scaling simply means multiplying with a scalar. And you can place your scalar anywhere, either before A, either after, before B, or before both of them. So it works that way. And you're saying that A cross A is always a 0. You cannot rotate two same vectors. So you cannot cross product two vectors. Remember, you said that you can do A dot A. You see that is possible, but this is not possible. So just remember. And you said what this is. Someone tell me, what do you say that A dot A it gives you? Someone respond by on chat or muting yourself. I don't know if I have allowed you to mute and mute yourself, but just write on chat. What is A dot A? We said it. Someone? Yeah, A squared, correct. That is true. So, Brian, thank you very much. Now, here is some other rules, some other axioms that we mentioned earlier. They are similar to those one of dot product, but they give you different results. We say that AX dot AY is equals to, somebody? Yeah, thank you, Gideji. That is understood. Thank you, Gideji. We have got it. So now we are talking about AX dot AY. We have said that this equals what? Now answer for this one. The axioms for dot. 0, correct. So that is 0, and therefore, but we are saying now that AX cross AY is equals to AZ. We actually follow something called cyclic permutation. And you see in a figure, shortly that they follow a very defined order. AY cross AZ is equals to AX, and AZ cross AX equals to AY. We are calling this a right-handed coordinate system. We are actually drawing them on a circle. They are following each other. just the way they follow each other on the alphabet. X, Y, Z. Assume that you're just forming a circle. After you have gone to Z, you go back to A. So like X, Y, Z, X, Y, Z, X, Y, Z. So like you are forming a loop. Therefore, you just need to say this, that if you are at AX, you go to AY, the next one will be AZ. You can take it that way. So it is like you're doing A cross, okay, AX cross AZ gives you AZ. Or you can even adopt this one that is right here, that AX cross AY is equals to AZ. AY cross AZ equals to AX. But the best one for me, I think I follow is the one that is following over circle. Okay, so like you assume you are putting a cross after everyone, after every okay, you are doing cross there. So you're doing AX cross AY is equals to AZ. Assume you are now doing this one, AY cross AZ is equals to AX. So that always has worked for me. You are moving in clockwise direction, and you are saying that the first one, the second one, the third one. So now here is the trick point. If you jump as we are going through the loop, it becomes negative result automatically. Like if you are saying AX, let me show you. Like say AX cross AZ, you jump to one, you jump to this one. So the result will be AX cross AZ, it will be equals to negative AY. Because you jumped it, it means that you get a negative. And that is always how they work. Because you're always going to the right. So if you have AY, let me draw another one. If you are here and you are here and then you jumped to AX, such that you have now AY cross AX. Because you jumped this guy, it becomes negative AZ. And that is simply what we mean by the cross product. And therefore, that is the rule we follow. You can always draw that diagram. It becomes rather straightforward. So these are the rules. We are saying that they follow some cyclic commutation, and we follow by that light hard rule, and it gives you that. So study that, and you'll see that it always works. We jump now to the scalar triple product. And I always allow people to ask any question, say something, understood. Someone can just say understood and then allow us to move on. People are dropping. By one, we should have finished, so don't drop. Someone say something without leaving the class. Somebody says, got you. Thank you, Brian. Thank you, Gideji. It's always good to have some response. Now, let's now jump to scalar triple product. And we want to say now that you have three vectors, A, B, and C, and you want to find out triple product. So triple product always involves one dot and one cross. And they take the shape that is given in question 1 to 9. So you only have either of these. Not all of them at the same time. So you can have that, you can have this other one, or you can have this other one. So if you have the first one, and I think I can briefly do this illustration. If you have A dot B cross C, we are saying that you can pick the last one and say what is this? Things are not moving as fast as I want them. C dot A cross B. Or you can pick this other last one again and you say B dot C cross A. Kimutai, you are distracting people by showing them your camera. So notice the idea I'm using, that I'm always picking the last one and then replace. I think I can draw another bracket. I'm replacing this last one. I pick it. This becomes a dot, but this becomes a cross. In that order. I pick this one. This becomes a dot, and this becomes a cross to have that one. Just a way of used to remember. But that is the idea of scalar triple product. And now we are going to say now that what is the significance of that scalar triple product? What is its significant or significance? If you are given that, you'd take your A to be your coefficient, and B becomes your B and C becomes the multiplicants, such that the result would follow the same thing that we have done earlier, like you cross this and this, you write is equals to AX, the one that you have put at the center, into bracket. What did I do? AX, it's supposed to be at there. AX, then BY, CZ, I started with this arrow as 1 minus BZ times CY. Now, notice that now all these have become scalars because the output of a scalar triple product is a scalar. That is why it's called scalar triple product, because the output is a scalar. So everything becomes a scalar and you just do the multiplication. Then you say plus AY. You remember that this now becomes 2, this becomes 1, the 2 becomes there. What you observe is that for AY, the two become, these two interchange. Therefore, we'll have, but now they are going to be crossing this one and that one. I think I can use a different color so that you can see the idea, what I'm saying. Let me use a red one. So we are going now to cross that and that. We have written our AY there, and then you're going to start with BZ becomes being our 1 and this being our 2. Therefore, we have BZ CX minus BX CZ plus AZ. I don't know, I'm not going to do that. All I'm saying that is how you do the scalar triple product. And that is enough said. So we can carry on to the vector triple product. And they're saying that we have 3 vectors. And this one they do not follow the one I had done for dot product, but they follow a rule that we call back curb. That you have A cross B cross C, and the bracket is between B and C. You actually have B into bracket A dot C minus C A dot B. And the output will be a vector. Because remember that the output of this bracket is what? The output of this one is a scalar. So scalar times a vector becomes a what? A vector, isn't it? Say yes. And this is a scalar again, the inside the bracket, and the outside is a vector. So when you multiply a vector with a scalar, the output becomes a vector. And therefore, the output of this vector product is a vector. And you're saying that it may be called, remembered as a backup rule. It should be noted that A cross B into bracket C is not the same as B dot C outer times A. Because the reason is this will be a vector, sorry, this will be a scalar, and this will be a scalar. So these are going to be two different scalars. And I'm back. Someone interrupted me and I couldn't see where this guy is. Now I have seen it. It was lost, it was hidden. Okay, so I was saying that this is a scalar and this is a scalar. Therefore, you cannot say that one vector multiplied by, these are different vectors. So these are two different vectors. Therefore, when you multiply them with two different scalars, they're going to give you different results. And that is why they are never the same. But you can put C before or after because it doesn't matter. Because the output of this one is a scalar, and therefore the scalar can be before a vector or after a vector, and doesn't really matter. This is the last point I want us to talk about. It is a component of a vector. And components of a vector are gives you the projection of a vector in a given another vector's direction. So here is the idea. I think I should actually jump to the example. So this example says the following: that this is vector A, this is vector B. I hope they still have numbers. That 10 of them have dropped. Okay. This is the last concept I want to talk about. That this is vector A and this is vector B. And the distance, of course, the angle between them is theta AB. If you are told to find the component of A along B, it will simply saying how much. Okay, I think I would better give you this idea. That you are in Nyeri here, telling you because that's where I am. You are in Nyeri, and you are going, one person is going towards Naivasha, another one is going to Nyahururu. And in few words, oh, I should have done it the other way. This is definitely not appropriate. So let me give you the, this is Nyahururu, and this is Naivasha. So we can see that Naivasha here is longer than Nyahururu. Therefore, we are saying that if you are going to Naivasha and you are passing through Nyahururu, what distance will you have covered? The distance of going to Nyahururu you have covered for you to before you reach Naivasha. And he's saying that it's simply this portion of the vector. So you have gone through here and you have gone through here. So this you not have covered, but you have covered between this point and this point. So that is the idea of the component of a vector. So we are saying that how much component of B does A cover along the direction of B. So that is the idea. So I want now to go back now to the real mathematics of this. Now you are tired also. I'm also tired. Just need to finish this one. That the vector, where did you start? That a direct application of a scalar product is its use in determining the projection of a vector in a given direction. Talking about projection or component. The projection can be a scalar or a vector. Given a vector A, we divide a scalar component AB of A along vector B, as we have seen in this diagram. Not wrapping. As fast I wanted to wrap. Okay, so we are defining our scalar AB in the direct in along AB, and we're asking ourselves, AB can be expressed in terms of B, how? And we can simply say that is equals to B equals to AB, or rather this AB here. This AB is simply a portion of A along B, and it is simply going to be given by the magnitude of A cos of theta AB. Look, think about it the way we used to do hypotenuse versus the opposite and the adjacent. If you want to express hypotenuse in terms of the adjacent, you'd simply say that that is a component of A along B. So the component of A along B is simply the magnitude of A, then along the direction of B, which is cos theta of AB. And similarly, we have seen that this AB becomes A cos theta AB, which is expressed as such, and again can be expressed as vector A dot vector AB. It's just simply mathematics to tell you that it will still become in this form. That is a scalar component AB. However, you might now want to say vector component AB of A along B is simply the scalar component multiplied by the unit vector of AB. What we got earlier here, you add the unit vector of AB of B, which is AB, and it simply becomes this. And as you can see, this will give you the vector because it is represented by the magnitude plus the unit vector AB. So in summary, both the scalar and vector components of A are illustrated in figure 10, like we have seen here. We notice from the figure 10b that the vector can be resolved into two orthogonal components. One component AB parallel to B. You can say this is two components. We can resolve this vector A into two orthogonal components, AB and A minus AB, perpendicular to B. In fact, our Cartesian representation of vector is essentially resolving the vector into three mutually orthogonal components. So it is like the example we had given earlier, like you are the way we do it in Cartesian coordinates. We normally have a point here. How much distance? This is vector RP. This was my P. We normally ask ourselves, how much we have gone along the X direction and along the Y direction to reach point P? So we are saying that this is the component in the X direction, and this is the component in the Y direction. That is simply what we are talking about, without doing so many mathematics like we have done. So I don't intend to do this example. I just intended to reach that point and say that I hope that is understood. I hope that is understood. You can look at the examples that are given and the exercises, and remind the members who are not in this class that I will be sending. I think I can stop sharing now, and I can also stop the recording. Where is it? I want to stop the recording.